All right. In module 6.06, we're going to cover scatterplots and line of best fit. Some of this is going to be a little familiar. If you're in my class, at least it should be. The part near the end, though, might be a little bit different. Talking about residuals, we haven't really done that before, but that might be the newest thing. But let's see what we have here. So the I guess the story it's telling us at the beginning here is it's got, talking about the New York City Marathon. And the marathon operators, or the people in charge of the marathon, want some kind of model that will predict how many runners there will be in future marathons. And so they need to figure out, using previous marathons data, like how many people attended last year, how many people attended the year before that, and so on. How can they take that information, make a model with it, also known as some kind of equation, and use that equation to help predict future numbers of runners, like how many runners are going to be in next year's or the year after that or in 20 years from now. Have a model that will predict how many runners will come to the marathon. So that's what this is going to tackle, right? We're going to try and figure out how to create an equation from just given data points so that we can model it and use it to make predictions. So for New York City Marathon, here are the past, I think, 30 years, it says, right? So in 1976, there were 2.1 thousand competitors. Keep in mind that all the numbers are in the thousands, right? And you can see year by year, 4.8 thousand, 9.8 thousand, 11.5 thousand, and so on. And as these numbers go up, 2006, all the way up to 38.4 thousand, right? So there's a lot of information. And it would be nice if we could take this information, graph it, and make a line that will predict what, trends is going in and what values or how many runners will be in the future, like 2010, 2020, 2030. So here's how we do it. First thing is creating a scatter plot. So obviously it's just, all it is just taking these points, these ordered pairs, and plotting them on a graph. Obviously, I'm not going to do that because there's 30 of them, but if you imagine taking all 30 of them, you can make a graph of it. Now, so you can see there's the graph there. Now, before you make a graph, what's important is if you do make a graph from scratch by hand, you want to make sure that the axis is good, right? So you determine the axis. So notice the x-axis, which is going to be year. The lowest is 1976, and it goes up to 2006. So what makes sense is if we had a graph, our x-axis going from maybe like 1970 all the way up to 2010. That way we can be sure that all these data points will fit in there, right? And you would do the same thing for the y-axis of your graph. You would look at the y values and try and think of a good range for them. So the y values, you'll see the smallest is 2.1, but then it goes all the way up to 38.4. So when you make your graph's y-axis, if you have to start at 2.1 and end up at 38.4, maybe going from 0 to 40 would be a good use of that axis, because then you can fit obviously 2.1 in and then all the way up to 38.4. So determine the axis is not a tricky thing. We've been doing that for a while, but it's really kind of just making sure you use values that make sense. I've seen some people turn in work where their axis doesn't make sense. For example, I've seen people who, on a problem like this, would maybe do their axis from 0 all the way up to 500. Now, why would that make any sense? For the y values, the competitors, the highest it goes is 38.4. So when you graph it, you're not even going to be like, up to here, because if you go by 500, that's going to be just huge. You're never going to use any of that space if you go all the way up to the hundreds. So, obviously only go up to 40 would be good. That way you can utilize your space more efficiently on your graph. So it's very important you choose values for your x and y axis kind of appropriately. Plot the ordered pairs, of course, as you know, when you graph anything, you just got to put the ordered pairs on the graph. So this is what all those ordered pairs from the New York City Marathon values, all these values plotted looks like. And then what do we notice? Well, we notice that there is a trend. It's kind of an upward trend. If I were trying to sketch a line through it, I would say a line goes this way. So you can tell that our line is going upwards. As we read this from the left side of the graph to the right side of the graph, our line is definitely going upwards. Let's look at, there's two types of correlation. There's I guess three types if you think about no correlation. But there's positive correlation, negative correlation, and no correlation. So positive correlation is when your data trends upwards. As the x values increase, so as these numbers get bigger, the y values get bigger with them. So that creates an upward pattern. A low x value means a low y value, but a higher x value corresponds with a higher y value. So they go up in unison with each other. A negative correlation will, of course, just do the exact opposite, in which case it will go downwards. So negative correlation, you can see a downward trend from left to right. And you'll notice here that as the x values increase, the y values will decrease. So a small x value will be really high up on the y-axis, a point up there, but a bigger x value, like 20, will have a much lower or smaller y value. So that's a negative correlation. As one value is increasing, the other is decreasing, and it creates a downward pattern. No correlation is pretty self-explanatory. You simply see no pattern in the data. There's nothing that ties any data points together. There's no trend, nothing more to it than that. All right, so developing a line of best fit. Now, we've done this before in class. What you would do is you would look at your graph of your data points, you plot it all, and you would try to sketch through it a line of best fit. So if I looked at this, obviously you want a very straight line, but it's going to be kind of hard with my computer here, but I'll try, right? I would draw a line that goes through the data as best as I can, right? As straight as I can. A lot of times, one common misconception is that people need to start at 0, 0 and make a line that starts at 0, 0. So like something like this. That's not true. You don't have to start at 0. You don't have to start there at all. You have to kind of just go with the flow of the line. So if the flow of the line doesn't flow towards 0, then don't start near 0. This one starts somewhere near 50 or 60. So I would make a line kind of like this. Right now, that's my line. Your line might be slightly different than mine, but it should be pretty close. So what type of correlation do we see? Well, in this one, because it's going upwards, very slightly upwards, but it is slanting upwards from left to right, we would say that this is a positive correlation. And again, the line of best fit, let's see how my line compares with theirs. Mine's a little different than theirs, of course, but it's roughly about the same. But so that line that we've drawn and the line that they've drawn, as you can see, that's their line of best fit. It's the line that they think best goes through the data points, best sort of maps them out or follows the trend of them. But what we need is an equation for this. So obviously, if this line were to continue in this direction, we can use it to make future predictions. So like if the x value were to continue going, and I was all the way up at 20 on the x-axis, I could use this line to sort of guess where the data points would be, assuming that the pattern were to continue following that line, right? So we want the equation of this line so that I can use it to make predictions on these future values. Trying to erase, but I just keep making more drawing stuff. All right. So that's the whole purpose of what we're going to try and do. We're going to try to write the equation of this line that we've drawn. And like I said, hopefully this might come back to you, seem familiar, because it is something we did in class before. So what we're going to need to know is slope formula. Again, here's the slope formula: y minus y on top, x minus x on bottom. Keep in mind that the y-intercept also can be used to predict the value at the beginning, because whatever the y-intercept is kind of where the start of your line is. So example, on this one, the y-intercept is about 50. So the start of that graph, or the beginning, was about 50. So at the decades after 1900, the life expectancy started at that time at about 50 years old, according to that graph. So how do we determine the line of best fit? Well, we take our line that we've drawn. So you can see they've got this one in this picture. I don't know. I can't blow it up or do anything there. But what they do, I'm going to snip this so I can zoom in on it a little bit better, is they'll look at their graph and they'll try to find 2 points to use on this graph. Now, they've come up with these 2 points, 1980 and 14. So 1980 and 14, it's about here. So they're going to use this ordered pair, that x and that y. And they're also using the point 2004, 37.3. So 2004 would be about here, 37.3. Yeah, 37.3, about there, right? I don't know how they're getting those values, but what you would do is you would look at your graph and try to find the values yourself that seem to be the best use. So these folks decided that these points were clear and obvious and good to use. But obviously, you can choose different points than a different classmate. So, but these points are what you would choose. Any points that you can find that are on this line are good points to use. So there's not just one correct choice, but here's 2, right? There's this is one point that they used on the line. This is another point that they used on the line. So now you use the slope formula and you try to find the slope. So that's simple. You just take the y value minus the y value, so 37.3 minus 14, and then the x value minus x value. So since we did the 37.3 minus the 14, we have to do 2004 minus 1980. So 2004 minus 1980. And what we get from that is, let's see, 23.3 over 2004, 24. And so when you calculate that, you end up with a decimal. It's about 0.97. So our slope is a decimal 0.97. And of course, you can see that's exactly the math that they did, right? They took the y minus the y on top, and the x minus the x on bottom. So they got 23.3 over 24 and 0.97. Now, to write the equation of the line, I'm going to do it a little bit differently than what they did. Because they use point slope form, and that's not the one that I would prefer. But this is their slope, okay? Be mindful of that. Slope is also known as the m value. Now, they use the point slope version of the equation. Some of you might be used to that, but so if you are used to it, then you can see exactly how they've done it. But I'm going to show you the way that I usually did it in my class, which is just using slope-intercept form. Slope-intercept form was y equals mx plus b. Now, I already know the m because we just calculated it, right? It was 0.97, so I know that this is going to be 0.97. But I also need the y and the x. Now, there are 2 points that were chosen, the 1980 14 and the 2004 13 or 37.3. So either of those will work. But those are, just pick one of them and then use the x and the y from them. So if we use 1980 and 14, 1980 is the x and 14 is the y. So I'll plug the 14 in for the y and the 1980 in for the x. So plug 14 in for the y and 1980 in for the x. Now you could have used the other point. It wouldn't have made any difference, the 2004 and the 37.3. You could have used that for the x and this for the y, and it still would give you the same result that this one does. So let's plug all those values in, right? I'm plugging 14 in for the y. I already know 0.97 for the m. I'm plugging in 1980 for the x. And then I just don't know b. That's the only thing I'm not plugging in anything for. Because my goal is to solve for b. So I plugged in the y, the m, and the x. So now I'm just going to solve for b. So what I'm going to do is I'm going to do 0.97 times 1980. So 0.97 times 1980, which is 1920.6. So we have 14 equals 1920.6. Plus b, of course. Now the b is still there, but we need to cancel this number out. So since it's positive, we'll subtract 1920.6 from both sides. So 14 minus 1920.6 is negative 1906.6. So that's what my b value is going to equal, since b is now all by itself. Now, since that's the b, and of course the 0.97 is the m, that means the equation would be y equals 0.97x minus 1906.6. There's your mx plus b, in this case minus b since it's a negative number. But that's our equation. That is the equation of the line of best fit that draws through here. So that blue line, that's the equation of that blue line. And you can see it's the exact same equation they found over here. There's just two different methods of using it. You can find it this way, or you can find it their way. Whichever one you find easier to work out. And so now you can use that line to make predictions. So I think that's what page 4 does. Yes, so here's your equation, right, of your line. And then you can now use it to make predictions. So if we want to know how many competitors will run in the 2010 marathon, that's from a different video, of course. So our equation was y equals 0.97x minus 1906.6. Right, so if I want to make a prediction about the 2010 marathon, 2010 is our x value, but I'm trying to figure out what's the y value of it. So I'm going to plug the 2010 in for the x value here. So that means once that's plugged in, the equation will be y equals 0.97 times 2010 minus 1906.6. So we just have to calculate this out now. So you take a calculator and you work it out. 0.97 times 2010 is 1949.7, but of course don't forget to subtract 1906.6 from that. So if you subtract 1906.6, you end up with y equals 43.1. So at 2010, you'll have, we guess, our prediction is 43.1 thousand. Okay, 1,000 runners. So you have your equation. Remember how we got it? Now, all we did here was we used the equation to help us make a prediction. So in the year 2010, how many people will run? And about 43.1 thousand people will run. So that's what they're doing here, simply just working that out. Now, in what year should the New York City Marathon expect to have 100,000 competitors? So here's how you would work this one out. So remember the equation, it's still the same equation, y equals 0.97x minus 1906.6. 100,000 competitors is our y value. We're asked what year, so what x value will that occur when we have 100,000 runners? Well, keep in mind that since we're plugging in 100,000 in for y, we're not actually plugging in 100,000. What we're doing is we're going to plug in 100 for y. Because if you remember, the original data points that we were given back on page 1 or page 2, the original data points, the original values, they all gave us the number in thousands. It didn't actually say, 2,100, right? It didn't actually say 38,400. It said 38.4, right? So that's the reason why we're not going to put 100,000 in here. We're just going to put 100 because it's already in thousands. So 100 to represent 100,000. So let's go back to the equation. So we're plugging in the 100 for the y to represent 100,000. So we still have the same equation, 0.97x minus 1906.6. So now we just have to solve for x. So that's simple enough. We'll add 1906.6 to both sides in order to cancel it out. So that's going to leave us with 2006.6 equal to 0.97x. And now we'll divide by the 0.97. And we'll end up with x equaling divided by x equaling 2068.6. So that means the year will roughly be the year 2068, or if you round up, the year 2069. So in 2069, there'll be 100,000 runners, which is crazy to think about. That's a lot of people. So that's let's see, what page are we on? Page 4. That's how they end up with, and they work it out right here. They've got the same answer we got. Okay, but then I showed you exactly how to get it. So now the residual. This is the thing that's kind of new for us. But before we get to calculating the residual, let's talk about other models. So nonlinear models would be a nonlinear equation. So obviously the problem we just did, the equation that we just found was a linear equation. But not a linear equation doesn't represent everything in the real world. So you can look at this graph, and you can see that this graph, its curve mimics something better than a line. It's not a straight line, so it's not linear. This curve really looks more of an exponential graph. We talked about that in a previous video. It starts off very shallow at the beginning, but then it gets higher and higher as it goes further and further. So this looks more like an exponential curve. So that's exactly what it's saying there. So an exponential equation is what you would want to write for a graph like this. But obviously, we're not going to write the exponential equation. I just want you to know that there are different models out there than just a linear one, than just a regular line. This one, to me, it doesn't really say what mathematical equation we use. You don't want to use a linear one because the data here is not a straight line. But my guess, and it's not exponential either, since exponential has an upwards curve to it like this. My guess is that this would really be better off maybe with a quadratic equation, but because quadratics have that parabola shape. But this just happens to be kind of like an upside down parabola shape. So like a negative quadratic, I think would be pretty good for this one. It's hard to say, but if I were to make a guess as to what model would work best, I would think that model would work the best for that particular one. All right, so now let's get into calculating residuals. So it's pretty simple. It just takes some time to do. So let me explain what's going on in this problem before we get to how you calculate this residual. So right here, this problem is setting you up with data points on height and weight. So it gives you someone's height and it gives you their weight. And then it plots all that data onto this graph. Now, we have nothing to do with residuals just yet. This is just taking the data points that are collected and plotting them on this graph. So then what you would do is what we just did last time, which is create an equation for this, right? Remember how you make an equation? You would just sketch a line of best fit through it, and then you would try to pick 2 points on that line of best fit to go, do the slope formula, y minus y, x minus x. You go through that whole process that we did with the New York City Marathon one. Let me see if I can go back to that work. Well, it's not on this one, but you saw earlier in the video how we wrote this equation, how we came up with this equation. You would do that exact same process for this graph. And so they've done that already. And they've come up with the equation of the y equals 2.8226x minus 80.4908. So they've already done the work for you to create this equation. So then what they've done is they took the height values and they plugged them into their equation to get out a y value from the equation. Because remember, a line of best fit is not going to go through every point perfectly. A line of best fit, some of the points are going to be a little bit off of it, right? Some of the points will be on it. Some of it will be above the line. Some of them will be below the line, right? It's going to change. So if you use the equation to find all the values, they're not always going to line up. So this is going to lag my computer a little bit, but I want to use the calculator on here to kind of help you see where they get all these numbers from. So again, apologize for the lagginess. So let me first, let's type in the equation. So their equation was 2.8226 times x, but I'm going to leave, well, yeah, we'll go ahead and put, right, times x minus 80.4908, right? So that's their equation. But of course, if you plug in certain values of x, like for example, the first value at 56, you can see it here, at 56 inches height, we know the real weight was 78. But using our equation, what does our equation give us? So let's type in 56. I'm going to insert 56 in for x, and we're going to calculate it. And it gets us 77.57. So that's where they're getting the value here, 77.57, right? Because they're taking this x value and they're plugging it into their model, their equation, to see what the y value is. So the predicted weight should be very close to the real weight, but again, sometimes it's going to be a little bit off. Like this one was a little bit less than the actual weight that was 78. And you can do that for all of these. You can plug the 52 in, this x value, and of course, when you do, if we go back here and we plug in the 52, the model, the equation gives us 66.28. Again, the same thing you see here. So it's not quite 63. In this case, it's a little bit higher than 63. But you see the difference, right? These numbers are all the actual weights from the data that we collected and graphed. And then the numbers below it are the weights that are predicted using the equation that we get. Okay? So these are the values you get when you actually plug all the x's into your equation. So now residual. Residual is the difference between the actual weight and the predicted weight. So for example, the actual weight for 56 height was 78, but the predicted value was 77.57. So the difference there is you just take 78 minus the 77.57, right? So you take the, let's do it over here, right? Take the real weight of 78 and subtract the equation's prediction, which was 77.5748, and you end up with 0.4252. That's this number here, right? So this is what the residual is. It's simply just taking the difference in the numbers, the actual weight minus the predicted weight. So you do that for each of these. 63 minus 66, of course, that's going to give you a negative residual. 67 minus 74.7522, that also gives you another negative residual, right? These residual values are just the actual weights subtracting the real or the predicted equation weights. Now, the idea is that when you add up all the residual numbers, so when you add up all those numbers together, you should have a number that's very, very close to 0. And in this case, they've already added them up. They've already taken all these numbers and added them together. And because some are positive, some are negative, that there's going to be some canceling out, right? And the idea is that it should be close to 0. So when you add up all the values that it gives you here, it adds up to 0.0124, which is very good. Well, what that means is that the closer this number can be to 0, the better your line is at predicting the value. So you want the residuals to all add up to essentially be 0, which then means your equation, the line, the prediction, this equation here, is a good equation. So hopefully that makes a little bit of sense as to what residual is. If it doesn't, please maybe rewind it and try listening to it again. Could help. All right, so activity 1, explain what type of model would work best. So again, based on this, it's not a straight line. It looks like it has an upward curvature to it. So what I would assume is maybe an exponential, and that's what it says, right? Exponential. So this one has a downward trend, but it is a very straight line. So I would say it's linear. I would say, of course, it's a negative linear correlation. It's a line that goes downwards. So yes, a linear model, since it's a line, and it's obviously a negative rate of change or negative slope since it's going downwards. So linear but negative correlation, negative linear equation. This one I would say has no correlation because there is no pattern to it, right? There is no trend, so no correlation would be a good answer for that. Activity 2. So here it's taking a look at the following scatter plot and which equation would be a good line of best fit. Let's see. So if we were to calculate this, let's try to calculate this the old-fashioned way, shall we? Now, the first thing that I would do is I would look at the 2 equations it's giving me and see if any of them seemed absurd. Now, neither of these seem absurd. The reason I think that is because plus 84, plus 92, these numbers would represent the y-intercept. And it's hard to tell, but 84, 92, it's probably something close to where they have it. So I wouldn't doubt either of those would be pretty accurate. What I'm looking for that would be odd is if this was like a plus 27, if the y-intercept was like plus 27, that would be really weird to me because I can clearly tell that my line wouldn't be crossing at 27, which is probably about here, right? So I'm looking to see if anything like that is odd, especially if it's a negative. If it was a minus 84 or a minus 92, that would mean its y-intercept is all the way down here in the negatives, which clearly is not on my graph. My graph does look like it crosses somewhere close to maybe 92 or 84. So it doesn't look too out of place, right? So neither equation looks bad from that perspective. The other thing I would look at is the slope. So this first equation has a slope of negative 10, and the second equation has a slope of negative 5. Again, none of those seem that strange. They both seem pretty reasonable. And the reason I say that is because the line that we see here is a negative line. It is going downwards. So the fact that these slopes are both negative in the equations makes sense to me. I would immediately rule out any equation that had a positive slope, though, because you can clearly tell from our line that it's a negative slope because it trends downwards in the left and right direction. If I had a positive slope in either one of these equations, a positive slope would be a line that goes upwards from left to right. So I'd immediately rule that out as a possibility. How could I have an equation with a positive slope if my line is clearly negative? So both of these are negative, though, which is why, like I said, nothing jumps out at me as being odd. So here's what we would do if we want to calculate. Let's find 2 points that are pretty much on this line. I would probably, it's really hard to say since you don't have actual data values, but let's say that maybe the point, let's try finding one at 5. 5, and I'm going to say maybe 570, right? That's kind of tricky. It's not very accurate because it's hard to really judge where the values are because it's not a very good graph, but I would say maybe 570. And then let's try maybe 10. And where does that go? Goes up to here. Let's see if I can make a straight line across. So I would say it's a little less than 50, so I'd maybe say 45. So 10, 45. And so what I would do is I would try to calculate the slope from those 2 points. So remember, slope is y minus y over x minus x. So our y values are 70 and 45, so we'll subtract those, 70 minus 45. And our x values are 5 and 10. So again, I'm taking this one minus this one, so I'm going to do 5 minus 10 here. So 5 minus 10. So we end up 70 minus 45 is 25, and 5 minus 10 is negative 5. So when I simplify this, this is simply negative 5. So my rate of change, or my slope, is negative 5. Now, immediately, what jumps out to me is I already have one of these equations down here already has a slope of negative 5. So that's the second one. So I would assume, without doing any further work, that that's probably a good equation to go with. But if we want to even try a step further, let's try to write the whole equation out, because we do need to practice that. Let's go with trying to make the actual equation of this line. So the m value is negative 5. Remember, we just calculated that. Now the y and the x, let's use one of the points. So remember, our points that we picked were 5 and 70 and 10 and 45. So let's pick any one of those. Let's pick the 5 and 70. So let's use the x. The 5 is the x. So we'll plug the 5 in for the x, and we'll plug the 70 in for the y. So I plugged in the y value, the m, and the x value. And now let's just find out what b is. Hopefully it's something close to 92. So when I do that, let's see, we'll have 70 equal to, this multiplies together to be negative 25. If we add 25 to both sides, then we end up with 70 plus 25, which is 95, equal to b. So the equation that I would make would be y equals mx plus b. Remember, m was negative 5. I found that earlier. Plus b, which would be plus 95. So this would be my equation, which is very, of course, it's very, very close to the one here. It's not plus 92, but it has the same slope and it has a very close y-intercept. So even though my equation is a little bit off, I would say that this equation is probably a good equation to use, or maybe the accurate one. Remember, mine was just based on kind of a quick glance and guess at the points on the graph there. So this one says it's a good possibility. What does this one say? I'm just out of curiosity. This says it would not be a good line of best fit. It's too steep. Again, you really wouldn't know that it's too steep unless you did the math that we did, right? I went out and I actually found points to find the slope. I didn't know the slope was going to be negative 5 just by looking at this picture. I knew the slope was negative 5 because I did the math. So it's hard to say it's too steep when you just don't do any math. All right, this one's tricky. This one doesn't really have a correlation. So I mean, whatever equation it gives me, I don't really know how accurate it could be, simply because I don't see a trend here. So this says, yeah, it would not be a good line of best fit because there clearly from the graph, it doesn't seem like there's much of a correlation there. All right, so we have a table representing studying minutes and test points, test grades. So make a scatter plot and draw the line of best fit. We're not going to make a scatter plot ourselves, so we'll just look at the one that they have. Hopefully it shows us one. It really doesn't, which is unfortunate. So there's not a whole lot we can do here, unless you have graph paper, which would be good. But yeah, I mean, they're going to get the equation of the line the exact same way that I just did on the last problem. Remember, you guys would graph these ordered pairs, and then you would try to pick two of them that appear close to the line and make the equation out of it. So they've made the equation this one, and then of course they can use it to make a prediction. So if they want to predict what a student will score if they study for 35 minutes, then they're simply going to plug the 35 in for the x value and see what the result is, which is what happens. They plug the 35 into their equation, and they got a y value of 81.09. Again, this would be a little more work if you are actually going to make that graph. And so now residuals. This is what I really wanted to talk about since it's kind of the newest thing. So this is asking if the equation that it would have given us would be an accurate one. And the way we could test to see if it's an accurate equation, which it doesn't give us an equation, I get that. There's no equation here. But we know the residuals that are based on the equation. So remember, the residuals are just taking the actual salaries and subtracting the predicted ones. So 31 minus 37 was -6. 35 minus 39 was -4, right? You get these residuals. So what they're going to do, what you should do is you add up all the residual numbers together. So -6 plus -4 plus 1 plus 5 plus 8 minus 4 minus 3 plus 7 plus 4 plus 4 plus 12 minus 8 minus 11, right? You add up all those numbers together. And when you do, all these numbers add up to being 25. Now that's a very bad thing because what we want is we want those numbers to add up pretty much to the number 0. We want to be very close to 0. So if the numbers add up and they're 25 as their total, that's not very close to 0, which means that the model would not be a very good model. So when you talk about residuals, the way you determine if it's a good model or not is if all the residual values add up to 0. If they add up to 25, like in this case, then it's not a good model. All right, that's well. Hold on, there's one more page. Let's see what's on here. Is there any goodies here before we take the quiz? Nope. Is there a page 7 then? Let's see, what does page 7 say? Oh, you have an assessment. Okay, so you guys have a project to do. Obviously pick project 1 or pick project 2, and that's what you'll be working on. I imagine it involves making a scatter plot, drawing the line of best fit. So exactly what we talked about in this video. So you're going to need to make a graph. You're going to need to pick points on that graph to find the slope, and then write the equation out. Remember, you use the slope, you plug in the values of a point into the equation to solve for b. You write your equation. Then you use that equation to make a prediction. You've done this project already, guys. I want to remind you of it. You've already done this. We did this slightly before, back in March, before all this stuff happened. So this isn't too terribly new, but if you're stuck on it, please let us know. And please quit Googling other answers. You guys did pretty good on the last one from not trying to cheat. But if you continue cheating, we have to continue giving 0. So please refrain from doing that. If you have questions about this assignment, asking, if you're not sure about what to do, just let us know. Okay, we're happy to help. Just ask us questions in the discussions tab. But I look forward to seeing your submissions and seeing you in the last video, 6.07. Have a good day, bye guys.